Hi everyone. Today here we are, and we are here. This is the last. This will be the last section for process, because we are here studying the processes and this kind of thing. Okay, we are here studying the processes and this kind of thing. So we started with isobaric process, isochoric process, isothermal process. Then we ended in adiabatic process. Now we are going to study the polytropic process. Okay, polytropic process, this is the process that will gather all these processes together. Okay, yeah, this is this polytropic process. So now let us work on it. Okay, polytropic process. You see, for polytropic process, everything will look like the adiabatic process, okay? Because the polytropic process, it is a process that accept, okay, all the process together. So it contains the, how can I say, the adiabatic, the isothermal, and all the process together. And the equation for polytropic process, as the name say, poly, this prefix poly, it used to say that we have more than one process. Okay, so this is the process that contain all the processes together, combined. And the governing equation for polytropic process, it is this one, PV to the power n is equal to C. Okay, PV raised to n is equal to C. For this polytropic process, okay, I told you that for polytropic process we can find every processes. See here, this n here, it is the polytropic index. It's like index of polytropic process. Okay, index for polytropic process. For polytropic process. Okay, this is the index for the polytropic process. See, that's why I told you that this guy contain all the process. Suppose when this n is equal to 0, let us just go for n equal to 0. When n is equal to 0, what's the process that we are going to have for n equal to 0? For n equal to 0, we will have this process here. P v to the power 0 is equal to C. So P v to the power 0, it is 1. So P equal to C. So it is isobaric process. Okay, this is isobaric process. So when the polytropic index is 0, we are in the presence of the isobaric process. Okay, now let us change. Let us see. Suppose for n equal to 1. Okay, so what will be? It will be P v raised to 1, okay, equal to C. If it is 1, so you got this one, P v equal to C. Which process is this? This is isothermal process. Okay, isothermal process. Isothermal process. Now, for n equal to infinite, okay, when n is infinite, okay, here if n is infinite, okay, let us just go for this one. Hey, this looks like it's impossible. It cannot be possible for this n equal to infinite. Nice, but it is not like this. Okay, yes, as I was saying, when n is infinite, what will happen here? See, you will get P v raised to n equal to C. Now I just suppose here, just put here for 2 states. Let us just write this like this one. So for n infinite here, if I put infinite, everything will be with no sense. Okay, so what do I have to do? If you put here infinite, it will be all infinite. C is not infinite. Okay, infinite is not a constant. So to make it sense, I have to go for these 2 processes. Okay, just add 2 processes there. Suppose in process 1 it is P1 V1 raised to n, okay, and P2 V2 raised to n. So what do you have here? P2 V2 raised to n, it's okay. Now divide it all by V, put everything that has n apart, okay? Like divide it all by, I want to take this one here and this one come here. It's very easy. Just come this one here and this come here. It's multiplying, go dividing. It's multiplying, go dividing. So I will get P1 upon P2 is equal to V2 raised to n upon V1 raised to n. So it will be P1 upon P2, okay, equal to V2, sorry, yes, V2 upon V1 raised to n. Now I just multiply, I just take this one here and just put here also this one, okay, just like that. I put 1 by n and 1 by n. It is like when I have 2 is equal to 2. If I put here 1 by 3 or 1 by n and here 1 by n, it will be the same. It's okay, it will be the same. So here it will be cancelled out, this one. So what will I get? I will get only P1 upon P2 to the power 1 by n is equal to V2 upon V1. Now see, if you put this n infinite here, 1 upon infinite, what will it be? 1 upon infinite is 0, okay? 1 upon infinite is 0. That's why you will get this one, okay? It means that V2 upon V1 will be equal to this 1 to the power 0. It will be P1 upon P2 to the power 0, raised to 0. And this will be V1 or V2 equal to 1 time, this is dividing, go there. It is multiplying V1. Because this one will be 1, so 1. It implies that V1 here, V2 is equal to V1. Which process is this? This is which process is this? V1 is equal to V2. So this is an isochoric process. So when n is infinite, we have isochoric process. Okay, V1 is equal to V2, and this is constant. This process is isochoric. Okay, when n is 0, isobaric process. When n is 1, isothermal process. When n is infinite, it is isochoric process. So if n is gamma, then we are in the presence of adiabatic process, just like this. Okay, yeah, just like this. That's why we say that polytropic process is the process that is containing all the process together. It's combining all the process together. That's why we can say, so PV raised to n is equal to C. N equal to 1. This is isothermal process. Isothermal process. N equal to 0. This is isobaric process. N equal to infinite. This is isochoric process. If n is equal to gamma, this is adiabatic process. Nice? Just like this one. Okay? That's why we call this polytropic process, because it contains in itself all these processes combined. And also, we can just draw the PV diagram for the whole process. Okay? What is the PV diagram for the whole processes? Here. Below, so this one, it is V and P. So pressure constant pressure and constant volume process. Okay, here n is equal to, when constant pressure is constant, 0, isobaric process. Here n is equal to infinite, okay, because it is constant volume process. Now here we have then when n is equal to 1, it is isothermal process. Okay, let me call this one, this is isothermal process. n is equal to 1. For n is equal to n, like n is equal to n, this will be like this. The greatest slope, this is n equal to 1, this is n is equal to n. The greatest slope is when n is adiabatic, okay? Because here n is equal to gamma, because gamma is a number greater than 1, okay? So this is the slope of entire processes, of the whole processes, of all the processes, like this one, okay? Okay, hope you can understand this one. It's okay? Now we are fine, we are okay. Now let us jump to find what is the relation PVT, what is PVT relation of this process, okay? What is PVT relation for, what is the name? PVT relation of polytropic process. Okay, PVT relation of polytropic process. See, for PVT relation of polytropic process, it will be the same as adiabatic process, all the same. We'll just have to substitute where you find gamma, put n. Okay, so for pressure PV, it will be PV to raised to n equal to C. For temperature and volume, it will be T times V raised to n minus 1 EC. And for temperature and pressure, it will be the same, T upon P to raised to n minus 1 upon this n. This is C. Okay? This will be the same. Nothing will change. Okay? What about this one is the PVT relation. Go. Okay, this will be the same. So what about for work done? Work done, okay, work done for this polytropic process. So the work done for polytropic process will be the same, okay, nothing will change. Will be the same as the adiabatic process. The only thing is that you will just change where you find gamma, you put n, okay. It will be P1 V1 minus P2 V2 upon n minus 1. Okay? Yeah, n minus 1, and that's all. So what will be our internal energy, delta U? The internal energy doesn't depend on the kind of process, so no, it only depends on the temperature. In this process, the temperature is changing? Yes, then internal energy is mCV delta T, the same. Okay? The same will happen with the change in enthalpy. Change in enthalpy will be P, okay, P2 V2 minus P1 V1, okay, plus U plus U2 minus U1, okay, just in this way. And then you get MI delta T plus MCV delta T. You will find the same equation as we have already find. R is what? R is Cp minus Cv delta T plus mCv delta T. So here you get mCp delta T minus mCv delta T plus mCv delta T. This and this will be cancelled out. So change in enthalpy will be only mCp delta T. Okay, will be the same guys here. You can see this is change in enthalpy. Now the only differences between them, okay, between the adiabatic and polytropic will be in the work done. Okay, not work done, in the heat transfer. So in polytropic process we have heat transfer, okay, and the heat transfer is different from what we know. Okay, now we are going to solve for heat transfer. Okay, so heat transfer for polytropic process. What is heat transfer? Okay, heat transfer heat transfer for polytropic process. What is heat transfer for polytropic process? We know that heat transfer, it is work done time delta U. We know what is this, we know what is this. Now we have just to calculate this one. This is the most important and interesting thing that I feel like, yeah, this is good. See, heat transfer will be work done. What is work done? Work done, it is P1 V1 minus P2 V2 upon N minus 1 plus M CV delta T. Is that okay? So the most important thing that we have to grab is work done for a polytropic process can be expressed as like this one, okay? Or you can express in terms of work done, okay? It like heat transfer can be expressed in terms of work done, or heat transfer can be expressed in terms of internal energy. First, we will apply for internal energy. Okay, wow, nice. See, here we know that P1 V1 minus P2 V2, it is the same. Nice, it is what? MRT1 minus MRT2. So I will just change the signal here. I will take out the signal. So I will have MRT2 minus P1. Okay. Yeah, MRT1, that should be MRT1 minus MRT2, but I just put out the signal, just factorize the signal, so I'll get MRT2 minus T1. This is delta T, okay? N minus 1 plus MCV delta T. Is that okay? Yes, it's okay. Now it is M, now MRT2, it will be MR delta T, okay? Upon N minus 1 plus M CV delta T. Just grab this expression from here. See, I want to express, suppose I know what is the work done, okay? Or suppose I know, in this case, I know the MCV delta T. Is that possible to find the heat transfer knowing only this expression, knowing only the internal energy? Is that possible? Yes, it is. Just substitute where is R, just put CP minus CV. Okay? Or we know CP minus CV, or we know if you just divide this expression, we have already derived this one. We know that R is equal what? Is equal to what? CV upon gamma minus 1. Okay, if you just divide it all by CV, and here CV, this is gamma, okay, this will be 1, okay, yeah, and this will be CV. It's okay, gamma minus 1 and CV is just on. Sorry, this is CV, here it is CV is equal to this R, okay. CV is R to this one. Okay? We know this. Okay? Just divide this one. So we can express CV with respect to R, or we can also, okay, we can also find R with respect to CV. This is CV gamma minus 1. It's just from here. Just if you divide here, divide it all by CV. What you get? You get R upon CV equal to CP upon CV minus 1. Then this is gamma minus 1. This is R upon CV. Just send this CV, it is multiplying, dividing, go there. It will be multiplying. So you get what? R is equal to CV gamma minus 1. Okay? And here also, from here you can also find CV, it's multiplying, go dividing. It will be R upon gamma minus 1. Okay, yeah, done. So if I want to find what is heat transfer with respect to internal energy, just change. Where you find R, put CV and gamma minus 1. Okay? Put there. What you get? You get this one, minus M R. What is R? CV gamma minus 1. So CV gamma minus 1 upon N minus 1 plus M CV delta T. And here it's also time delta T. I forgot. Okay? Time delta T. Okay? This delta T, delta T. Now from here, what you get? See, this guy, okay, just take comma, mcv delta t, mcv delta t, take it comma, okay, just take it comma, mcv delta t. You will get what? Minus, okay, this one, minus gamma minus 1 upon n minus 1 plus 1, okay. Then from here, just work out on this. You will get what? You will get mcv delta t, okay. And this guy, find the common denominator. This is simple math. You will end in this one. You will end with this one. N minus gamma upon n minus 1. This will be heat transfer with respect to, what is this? mcv delta t. This is the same as delta U. So it will be delta U time n minus gamma upon n minus 1. Just like this. Okay? Just like this. Now, Veloso, how if I want to find what is the work done with respect to work done? Very simple. Finding work done with respect to this guy, just substitute where you find CV, put R upon gamma. We will do this one. Okay. We will do this one. So, okay. So, okay. Hey, we are running out of paper now. No more paper. Okay. I could find some papers here. Okay. See, I could find some papers here. It's okay. See, okay, now we are going to find what is heat transfer with respect to work done. Okay. You remember this, okay? We will start from here. From here, okay? This is minus mr delta t upon n minus 1 plus mcv delta t. From here, okay, you can see let's substitute this one. So see, as we said, okay, we will just use this expression. I want to express with respect to work done, so there must have R. So I have just to substitute where I find CV, I put R upon gamma minus 1. Okay. Just put here CV is equal to R upon gamma minus 1. Okay, then just put here Q will be minus M R delta T upon N minus 1 plus M. What is CV? R upon gamma minus 1. Then delta T. Q will be this one and this one. Okay, what will I do? Minus M R delta T upon n minus 1 plus mr delta t, okay, and here gamma minus 1. See, I have just to substitute, take this out as common, mr delta t common, this will be minus 1 upon n minus 1 plus 1 upon gamma minus 1. So this will be mr delta t, this mr delta t, what is this? This is the work done, okay. This is, this is not directly the work done, okay. But yeah, because work done is negative, nice, okay. So if the work done is negative, I have to consider this minus. This minus can take out this minus here, keep here the same, okay. Because work done is negative mRT, okay. Just put here like this one, It's nice? Yeah. Okay. Keep this minus MRT. Take this minus, pick up this minus, pick up. So just take comma as minus MR delta T. Here it will be positive, negative, because it is positive. Okay? Take this comma. Take this one. Minus, take comma, and MRT, take comma. Take comma, MRT will be out, and here minus and plus will be minus. So this will be like this one. Okay? If you play the sign of this and this will be minus, this and this will be positive. It will be go back the same. This will be minus MRT. Then from here just find the common denominator, and this will be easy. This and this and this. So this will be what? Gamma minus 1 minus n minus 1. Okay? And here you got n minus 1, and here gamma minus 1. Here what will you get directly? Okay, just apply everything you feel like. Okay, just solve this one. So here it will get, this is what? This is work done. Okay, time, and here you get minus 1 and plus 1. This will be gamma minus n upon, okay, upon, this is sorry, not this one. Okay, this is minus mr delta t. Okay, minus mr delta t will be equal to, see this one, this will be gamma minus n upon n minus 1 time gamma minus 1. See, gamma minus 1, see like this one. See, the work done, it is what? Work done is minus mr delta t n minus 1. So take this out. Take this n minus 1 out here. So it will be minus mr delta t upon n minus 1. This is work done. And this will be gamma minus n. Okay, gamma minus n upon gamma minus 1. Okay, so this is work done for polytropic process. So this will be gamma minus n upon gamma minus 1. Okay, so heat transfer can be expressed with respect to work done and with respect to internal energy, delta U. With internal energy it will be this one, n minus gamma, n minus 1. Yeah, and they are almost the same if you check, okay? They are almost the same. So now we are done with all the processes. I hope you may enjoy these classes, okay? So God bless us, and we are together. And for the next video, I'm going to derive the Otto cycle. Now that we know all this process, we know how to derive the Otto cycle. Thank you very much. See you when I see you. BME is fine. Fun also.